For the exercise 2.1, we calculated a principal component analysis, so PCA, on the HGC dataset, and then we stored the first two principal components in a file together with the clinical data. This looks like this then. So we have here the 19 controls and the 19 HGC samples, the group, the patient number, then the two PC1 and PC2, and the clinical data. You may see that here for the controls, some clinical data is not available because, for example, the control sample C1 does not have tumor staging. Only the HCC samples have that, for example. Okay, so we have to do a PCA plot now, which is a scatter plot of these two principal components. And we have different variations. So we color it by the group, color it by group, and have the point size by age, and have the point shape by group and the color by age. So these are three different variations. So this code here is how we calculated the PCA. I will not get into detail for that, but simple load the dataset that we have, that we saw in Excel, and then we have the three different plots. So we use ggplot function, and then the mapping differs. We have x and y for the first and second principal component. And then in the first variation, we have color for the group variable. You can see here that you can also see difference between the control group, which is more here in the upper part, and the HCC group, which is in the lower part of the plot. Now we use the size of the data points for the column H and color for group. And you can see here that we have now different sizes. So we have very small data points here that are below 30 years, and we have large points which are maybe around 70. But you can also see that it's really difficult to actually, know which age this is here just by comparing with this legend. So it's not that easy to see. Now we have shape for the group and color for age. And this is a bit better visible. So we have here lighter blue for higher ages, really dark blue for young people, and we have circles for control group and triangles for the HCC group. For exercise 2.2, we also do a scatter plot, but it's to compare two proteins with each other. We have a separate file, which I can show you here, which basically is a long format, kind of, but it has two columns for two proteins with their log2 transformed intensities that we want to compare. And we also have the age, the gender, and the group of the specific patient. So now we want to plot the log intensities of the first protein to those of the second protein, add a linear model to this relationship, and then create again the same plot but with separate models for control and HCC. As advanced exercises, the question is if there are other options to achieve the separate models and how you can create this data set from actually the long data set. Okay, so we read in the data again, which you can see here. We use a normal scatter plot, so the mapping is that we use one of the proteins on the x-axis, one on the y-axis, have the geom point, and then have the geom smooth to add the linear model. You can do it like this here. You see it adds a linear model as a blue line, but here it has a linear model actually over the whole data set. So now we want to have separate models for each group, and there are different methods to do that. We can achieve this, for example, by using coloring. So we color by group, and this will actually lead to an automatic separation of the linear models. And you see also that the linear models are quite different. So the slope is different, for example, for the C and the HCC group. We can also achieve separate models by using different shapes for the groups. This will also lead to two separate models, but you cannot really see directly very well which model belongs to which data points. We can also do it completely without using any tricks on shapes and colors. This is what the group aesthetic is for. So if we use group as group, we will also get two separate models, but you again cannot see really what is happening. So I think the best option is to use the coloring. Then you can directly see which data points belongs to which linear model. And here's some code to see how we generated this data set. So we basically filtered this long data set for these two proteins. And then we actually did a pivot wider function to actually split the information on these two proteins to two separate columns. In this case here, for example, the ID columns are everything we want to keep. So the name, the group, the gender, and the age. In exercise 2.3, we also do a scatter plot, but this time a volcano plot. So we use the dataset we generated and pre-processed in exercise 1.3 called data HCC volcano, which is also available in the data folder. And then we generate a quite simple volcano plot by plotting the log2 fold change against the minus log2 p-values, and then color it by the Euclidean distance. And we want to make the data points that are not significant transparent to like put them a bit into the background. So we open the data set and read it into R. And we can do a simple volcano plot with a geom point, and we have the following mapping. So the x-axis is the log2 fold change, the y-axis is the minus log10 p-value, color is the Euclidean distance, and alpha is this column here, which says a plus or a minus, whether it is significant or not. And if we do this, we can see here, we have this volcano plot. All the not significant proteins are have a low transparency, so a low alpha value, and the ones that are up or down regulated are blue, and depending on the Euclidean distance, so the ones with the high Euclidean distance like this ones or this ones are light blue, and the ones with the low Euclidean distance are dark blue. And you also get here a warning that using alpha for discrete variables is not advised. In this case here we knew what we are doing, but yeah, maybe it's not the very best way to use it in other contexts.